Hello. Now we will study the drift velocity, concept of drift velocity. So let's talk about this conductor. There is this conductor, and right now it is not connected with any external source. The battery is there, but it is not connected. It's open. So since this is a conductor, inside the conductor there are a lot of free electrons. And when we talk about the free electron, these free electrons, they keep moving in random directions with very high velocity actually. These free electrons, they keep moving in random directions. And their velocity is very high. Okay. But the thing is, when they are moving, they continuously keep changing their directions as well, because there is a very large force acts between these electrons. So at any point of time, if I want to calculate the average velocity of these electrons, if I want to calculate, that will be equals to Vi dni divided by dni, where I will be equals to 1 to infinity, because there are, we can say, infinite electrons. So here the n is the number of electrons. I'll let you know. The thing is, I'm assuming there are ni number of electrons which are moving with Vi velocity, and as the I value will keep changing, the Vi value will keep changing. So there will be some n1 number of electrons will be there, which will be moving, let's say, along x-axis. There will be n2 number of electrons will be there, which will be moving along y-axis. There will be n3 number of electrons will be there, which will be moving in any random direction. So that's how it will go on. And when you will calculate the average velocity for all these electrons inside this conductor, that will come out to be 0, because the motion is completely random. And there is no external influence onto the electrons. Okay. Now when you connect this conductor with the external source by closing this key, so this external source, which is the battery, now it is connected, and because of this battery, there will be electric field induced inside the conductor. There will be electric field which will be generated inside the conductor. Now I'll show it here on this side. So due to this electric field, each and every electron will experience some force, electrostatic force, and the value of force experienced by these electrons, these electrons will be equals to E times of E, negative. Because see, the force experienced by the negative charge particle will be opposite to the direction of electric field. So it will be equals to minus of E times of E. That much force each and every electron will experience. And due to this force experienced by the electron, it will start performing some acceleration. So the acceleration experienced by the electrons will be equals to minus of E by me times of E. That much acceleration the electrons will experience. Each and every electron will experience that much acceleration. Now, due to this acceleration, now earlier they were moving in random directions. Now they are experiencing a force, and because of that force, they will start feeling a drag. Drag means the particle which was moving in the same direction as the acceleration, its velocity will increase. But the particle which was moving to the opposite direction of acceleration, its velocity, obviously its direction of velocity is not going to change, but the magnitude of its velocity will decrease. So you will see some change in velocity supporting the acceleration. So in the direction of acceleration, net acceleration, electrons will start gaining the velocity in that direction, and their velocity will start reducing in opposite direction. Okay. So that will be the acceleration experienced by different electrons. That will be the acceleration experienced by different electrons. Now, due to that acceleration, now we want to calculate their velocities, or we can say change in velocity. So we know that acceleration can be written as dv by dt. Since acceleration can be written as dv by dt, so it will be E upon me E. And that value will lead towards dv is equals to minus of E by me, capital E, dt. Each and every electron will have the same charge, will have the same mass, and it will experience the same electric field. So all these values will be same. Now to calculate the change in velocity or the final velocity for these electrons, we will have to integrate that equation. So it will be integration of dv, and that is equals to minus of E upon me integration of dt. Okay. So the initial velocity for these electrons, I am calling that velocity as ui. since we are talking about the ith electron, there are a number of electrons, and the same equation will be applicable. This same equation will be applicable for each and every electron. So the lower limit, basically, I am talking about the individual particles. So some ith electron, initially it was having ui velocity, and its final velocity becomes vi due to this in 0 to t time. So the velocity of electron will be equals to vi minus of ui, and that will be equals to minus e me times of t. Or we can say it will become vi will be equals to ui minus of e upon me times of t. That will become the velocity of ith electron after experiencing this force. Okay. So now in this case, if I want to calculate the average velocity, now again I want to calculate the average velocity. This is the velocity when there was initial velocity, when there was no external force. This is the velocity when there is an external force in terms of electric field. So if I take the integration, if I want to calculate the average value of this, so vi average value of electron will be equals to average value of velocity initially minus of E upon me, and you see this value, this whole value is constant for each and every electron, so it will be average value of time. Now this is the velocity, this was the velocity of electron before the external source was applied, external force was applied, and this velocity we already know it was 0 in the beginning, so this whole value will be 0. So the average velocity for each and every electron will be E upon me t average, and the t average we define as tau. And this velocity, which is the average velocity, now this average velocity after applying the external force is not 0. And this velocity, average velocity of the electrons or average velocity of the charged particle after applying the external source is defined as drift velocity. This is defined as drift velocity. We call it by Vd. So this value Vd will be equals to, I'm talking about the magnitude now because the direction of electron you can define. Vd will be equals to E divided by me tau. This is defined as relaxation time. This tau is defined as relaxation time. What is relaxation time? So what happened actually during this motion, even when you see this, when you calculate this drift velocity, the value of drift velocity is very small compared to the actual velocity of the electron. So when we talk about the actual velocities of the electron, it is in the range of 10 to the power 5 meter per second. The instantaneous velocities of electrons is in the range of 10 to the power 5 meter per second. And when you calculate the drift velocity, that comes out to be in the range of centimeter per second, sometimes 10 centimeter per second, 50 centimeter per second. So you see, the Vd is very small. Now, why it is very small? When you look at the electrons, they are moving very fast. But due to this electric field, their velocities slightly increase in the direction of force and slightly decrease in opposite direction of force. It's a slight change which happened. But random nature of motion of electron does not stop. Electrons keep moving in a random direction. So in a sense, I can say if there was an electron which was moving in this direction, and before you apply this external agent, after some time it was supposed to change its direction. Due to the collision, due to the intermolecular forces, it was supposed to change the direction like these electrons. They were moving there, then they were moving that. All the values of these velocities, they were random. So electron was moving right, then again left, then again up, then again down. That's which was happening earlier. The same thing will be keep happening now also. So electron which was moving in the same direction, due to this external agent, its speed will be slightly increased. But again, after a movement, it will again change its velocity. its direction will be changed. The thing is, when it is changing the direction, obviously in earlier case when it was changing the direction, the magnitude was little bit higher. But in this case, the magnitude will be little bit lesser than the previous case if the direction is opposite. So it's still changing its direction. So this electron, it is moving in a single direction for a very small period of time, and within that time it is changing the direction. When the electron is moving in a single direction, that time, very small time, is defined as relaxation time. So this time is this relaxation time is the time during within this time the electron is supposed to change its direction. So only for this time the motion of electron will remain linear, and we have used the linear equations actually. So within this time the motion of electron will remain linear. After that it will immediately change its direction, then again for some time it will remain linear, again this time, then again it will change its direction. So when we are studying the VD, when we are calculating the this drift velocity, we bound ourselves only for this relaxation time, we call it tau. So this VD we calculate corresponding to the average velocity. This electron will gain the average velocity when you apply the external source only for this small time, and this average velocity, value of average velocity, comes out to be small e, which is a charge, capital E, which is the electric field, value of electric field, divided by me, which is the mass of the electron, multiplied with tau. Okay, and this tau also, we can define this tau as lambda upon VD as well. This lambda is defined as mean free path. The mean free path means, you see, when the motion of electron is linear, it is linear for time tau. And when it is linear, it will be converting, it will be crossing some distance. And the distance covered by the electron during that time is defined as mean free path. So if I'm having an electron, and starts from A, and it moves in a straight line till point B. So if this is t is equals to 0, it is moving in straight line, then t is equals to tau time, it will keep moving in a straight line. And the distance it will cover during that time will be defined as tau, and during that time its speed will be Vd. And the moment it will reach the B, time is up, distance is up, it will change its direction. And again, for further time tau, it will keep moving in a straight line, then again it will change the direction. So every time it is performing a straight line motion, it is supposed to cover the distance tau, lambda distance will supposed to cover, and for time tau. And during that time its average velocity will be Vd. That's how we define this. Lambda is mean free path. Till the time it's a distance electron covers before further collision. Some people say collision, but in reality collision never happens. It's the distance it covers till it experiences some obstacle. Obstacle can be the force obstacle, it can be some other field of obstacle. Then again it changes the direction. So this is one of the formula. We can memorize this formula, and this formula also we can memorize. And if you see these two results, by comparing these two results, I can get the value of lambda as well. If I compare these two results, I'll be getting the value of lambda as well. Okay, so sorry, no, we'll not be getting the value. This is the result we'll memorize, and this is also one of the results we will be memorizing. Okay, thank you.